Greetings from Washington State. You welcomed me, Denver, with a rainstorm where my airplane got sidetracked to Cheyenne, Wyoming yesterday. And we sat on the tarmac for 3 hours waiting for the okay to land into Denver. So we finally got into Denver, and then there was no gate available for the plane to park. So another 45 minutes on the tarmac in Denver. Finally got into my room a little bit after midnight last night. So if I fall asleep tonight, you know why. Regarding my website, there it is. I'm sorry for the right angle orientation of my website there, biblicalchristianworldview.net. If you go ahead and click on that link, it's on the website for the Rocky Mountain. Is it Christian Fellowship? Creation Fellowship, excuse me. RC. Okay, all right, gotcha. It's there, and you can click on it. So when you get to my home page, just click on the link called Mathematics, and then click on another link called Why I Wrote Mathematics is God Silent, and you'll see a link to order it. So you have to go through several levels to get to it. I apologize for not bringing a copy. I just didn't think of it. So that's pretty bad for an author not to bring a copy of his book. So there's a reason why professors are called absent-minded, so sorry for that. Now we're going to talk about a mystery story tonight. We all like mysteries. We all like Sherlock Holmes. We like, when I was young, I read the Hardy Boys series. I loved it. It was a page-turner, couldn't wait till the next chapter. So we all like mysteries. And we want to find out who did it. We like the investigation, we like the evidence uncovered, we like the analysis, we like the conclusion. So we're going to talk about a grand mystery tonight, a mystery that has been a conundrum to a great many well-known mathematicians, scientists, philosophers. And I'm going to introduce this mystery by one of the most well-known scientists, at least in the 20th century, Albert Einstein. And he said this in the 1930s. Just one simple sentence. He said, "The eternal mystery of the world is its comprehensibility." He was stunned by the fact that we as scientists could understand anything about the universe. He didn't have a reason to justify the ability to comprehend the universe. So this is one example. I'll give you a few more mathematicians and scientists to substantiate what Einstein was saying. But science is basically baffled by this. Philosophers of science and scientists. They're baffled not only by the existence of an intelligible universe, but also by the fact that the forms of thought that arise within the minds of scientists enable science to grasp the reality and intelligibility of the universe. Now, mathematics is a key player in this whole situation. I'm sure we've all went to school and we've all taken math classes and gone to university, some of us, and we always could see the math guy over there and says, that guy's, he knows how to do math. He's smart. He's one of those smart guys. He can solve those equations. And so mathematics is really a commentary on intelligibility. You have to follow a certain language in a certain way, order and operations to solve equations. So mathematics is a key player in this mystery, and I'll have a few quotes here that exemplify this. Richard Courant, a famous mathematician, early 20th century, said this: "That mathematics, an emanation of the human mind, should serve so effectively for the description and understanding of the physical world is a challenging fact that has rightly attracted the concern of philosophers." Solomon Bochner, another mathematician, says, "What makes mathematics so effective when it enters science is a mystery of mysteries." So there is mystery compounded. John W.N. Sullivan, a philosopher, says this: "Why the external should obey the laws of logic. Why, in fact, science should be possible is not at all an easy question to answer. Nicolas Bourbaki, a very famous French quote-unquote mathematician, he really wasn't a person, so five French mathematicians in the 1950s took up the pseudonym Nicolas Bourbaki, and they wrote in his name. How about that for an interesting person? And so Nicolas, quote-unquote, said this: mathematics appears thus as a storehouse of abstract forms. And it so happens, without our knowing why, that certain aspects of empirical reality fit themselves into these forms as if through a kind of pre-adaptation. Very telling quote by Bourbaki. And then finally, from a current living mathematician, Marcus Francis du Sautoy, a mathematician, Oxford University, says this. And he doesn't use the word miracle or mystery, he uses the word bizarre. The bizarre thing that is that the more abstract and difficult mathematics becomes, the more it seems to have applications in the real world. End of quote. And I could multiply these quotes 1,000-fold, and some of these are in my book. Some of these aren't because I continue doing research. Now, what I'm going to do tonight is I'm going to look at several topics, and I'm going to walk through them for you before I actually go through them. The first thing we'll look at, kind of a general outline, is the unrelenting issue that Einstein referred to, the unrelenting issue of intelligibility. Then we'll see the role of mathematics in its revelation of this intelligibility. We'll see how mathematics is used to describe the physical world, to explain how the world works, and to predict things in the world. And we'll see how mathematics has actually been used to discover certain aspects of the physical reality. Math alone by itself, discovering real issues, real things in the created world. And then we'll look at naturalism, which is what most modern scientists embrace, and their glaring silence as to the reason why this works, as we've illustrated by these quotes. And then we'll look at the beauty of mathematics and the deep nature of that beauty. And then we'll try to answer the question, why does mathematics work? And I'll give you a few hints to that answer, because we have to have a story where we give hints, and so you come to the conclusion, aha, the aha moment. Okay, so let's first look at the unrelenting issue of intelligibility. Thomas F. Torrance says this in his essay entitled Einstein and God. He referred to Einstein. Einstein remained throughout his life unabated, in an unabated wonder at the immensity, unity, rational harmony, and mathematical beauty of the universe. Einstein himself said this: the faith that I have is a faith in the possibility that the regulations valid for the world of existence are rational, that is, comprehensible to reason. I cannot conceive of a genuine scientist without that profound faith. So there was a faith commitment that undergirded Einstein's work. Theoretical physicist and Anglican priest John Polkinghorne said this: science does not explain the mathematical intelligibility of the physical world because it is a part of science's founding faith that it is so. So my question is there a justification? Not just for the intelligibility of the universe, but also is there a justification for the intelligent human scientists and their knowledge of the universe? We have two justifications we have to account for. Another way to answer this question, using a different terminology that comes from the computer world, what is the reason for the universe that we are encountering that is what I call user-friendly? Another way to say it, what is the reason for this well-coordinated universe? What is the reason for this universe consisting of the interconnectedness of the totality of things. Things going on outside my mind and things going on inside my mind. And all this plays into this final question in reference to mathematics. Is there a reason why mathematics works so effectively in the applications and discoveries of science? So is there some direction we can turn to get sufficient answers? At this point, I'm going to introduce ourselves to the answers that naturalism gives us to this question. Well, we've seen the answers, haven't we? There are no answers. It's bizarre. It's a mystery. I'm confounded by this. And so naturalism, based upon natural selection, has no sufficient answer. In fact, the biologist George Gaylord Simpson said this, and I quote, "We are the product of a mindless and purposeless natural process which did not have us in mind." End of quote. So it's interesting to note how these scientists use their intelligence to come to the conclusion that mindless matter is the source for all that there is. It's an interesting schizophrenic position that's taken. So here's my equation. You've probably heard the equation before, stated in different ways. Time plus matter plus chance. Now, that's how I used to hear the equation. But now, the new atheist, like Richard Dawkins, he doesn't like the word chance, and so he's changed the word to not use. He doesn't want to use the word chance, so he uses the phrase unguided natural processes. Well, that means the same thing. He just doesn't want to use chance. So we have time plus matter, got the equation, plus unguided natural processes. In my interpretation of those three variables in the equation, it's a cosmic crap game. Throw the dice and see what happens. That cannot equal the intricate complexity and rationality and ordered universe that, as I've already said, is user-friendly. Given time, of course, the scientist, the evolutionary scientist, because he has to have a lot of time, so he thinks he gives us lots of time, 15 billion years worth. He thinks that's enough. Given enough time, anything can happen. That's the statement. So, given enough time plus matter plus unguided natural processes, given that situation, nothing should be comprehensible. Absolutely nothing. There should be no coherence between thought and the physical world, given this premise. But this coherence exists. Hence, naturalism must embrace blind faith. And if you quiz them, a naturalist, long enough, as I have done in several instances, they end up by saying, well, it just has to be this. Oh, in other words, this is a statement of faith that you don't have no justification for this. They have to say finally at the end, yes. Now, the new atheists, as I've talked about, Richard Dawkins is one, the classic one, affirm that this order, in one of his books, he affirms this, only looks like order. And there is really no order behind the facade of order. That's what he's saying. But they have to assume the order to do any real science. But they can't admit that it's there. It's like the old smiling cat that disappears. So my question is, the whole structure of modern science has been built on an illusion? British theologian Keith Ward says this: to the majority of those who've reflected deeply and written about the origin of the universe, it is seen that it points beyond itself to a source which is non-physical and of great intelligence and power. The universe is not self-explanatory. It requires some explanation beyond itself. End of quote. In other words, what Keith Ward is saying is that the universe does not generate rationality. It only reveals it. And therefore, there must be a transcendent source for this rationality. The physical world is ordered in such a way as to be accessible by mathematics. And of course, this mathematics is created by mathematicians. And the mathematician has what I like to call a sixth sense. We all know about our five senses. Well, there's a sixth sense that the mathematician has. It's the ability to think mathematically and derive theorems and develop formulas that follow logical order. And so there's a sixth sense that he has. And what happens is that this great scheme of things, what we call the universe, and the human species that is in this universe is marked off as special by this sixth sense. In other words, there is a connection between the workings of the human mind and the workings of the physical world, especially as we look at the mathematical thinking of the human mind. Oxford University mathematician John Lennox, he teaches at the same university as Richard Dawkins does, and also Marcus du Sautoy. He says this: the intelligibility of the universe is grounded in the intelligence of the God who created both it and the human mind. Hence, it is not surprising that mathematical theories spun by creative human minds, themselves created in the image of God, find ready application in a universe whose architect was that same Creator God. So that's the issue, the unrelenting issue of intelligibility. Let's now look at the role of mathematics in more detail in its revelation of this intelligibility. Philosopher Mark Steiner says this: in formulating conjectures, the working physicist is gripped by the conviction, both explicitly and implicitly, that the ultimate language of the universe is that of the mathematician. In other words, mathematics is the gate and key of the sciences. Well, Steiner wasn't the first fellow who said that. Roger Bacon said that back in the 13th century. Without it, without mathematics, the scientist walks about in a dark labyrinth. Again, that's not original. Galileo said that in the 17th century. So here is what is happening with mathematics. I'm going to give you 4 points to try to bring together, and then I'm going to give you some examples. Mathematical concepts, as I look at the history of math and how mathematicians think, etc., mathematical concepts sometimes arise from physical problems. Not all the time, but sometimes they do. But they always arise from an impulse for beauty. You ask any mathematician who knows what he's doing, and you ask him the question, why are you a mathematician? And he will answer, because it is beautiful. Now, of course, you probably ask yourself, it's beautiful? What planet are you coming from? Not the way it was taught me. Okay. Unfortunately, there are not too many gifted teachers who know how to teach that beauty. And that's the bane of our education system. Well, that is what happens in terms of, that's why they are doing what they are doing. Now, philosopher Paul Valery says this: the universe is built on a plan of profound symmetry. Symmetry is another word for beauty, of which is somehow present in the inner structure of our intellect. There's a connection between the beauty of the universe. Now, I said the word symmetry. You can use that as a synonym for beauty. The mathematics of symmetry is just wonderful when you investigate it. You think about the symmetry of the human body. It's beautiful because it's symmetric. If someone's missing an ear or missing an eye, we say something is out of kilter here. That's not the way God designed it. So there's symmetry throughout the whole creation. There's geometrical symmetry. There's algebraic symmetry. There's just a whole host of it. Also, another word for beauty is logical coherence. Elegance, structure, architecture, systems. If any of you studied advanced mathematics, you probably studied groups, fields, and rings. It may sound familiar to some of you. That's all the structure, studying the structure of the way the order of mathematics works, the rational order, seeing the whole system as a huge architecture. I'm going to exemplify this quote a little bit later, but it's from the mathematician Jerry B. King. He says this: "The motivation for the development of mathematics is primarily aesthetic, not utilitarian. Beauty is what drives the discoveries and the work." That's the first point. Mathematical concepts sometimes arise from physical problems, but they always arise from an impulse for beauty. Second point: it is unreasonable to expect, as we've seen on naturalistic grounds, that what arises from the impulse for beauty should be significantly effective in physics. Why should that be? All right, that's point number two. Point number three: but a significant number of these concepts that arise out of beauty, the desire for beauty, are significantly effective in physics. That's the big but, number three. And number four: hence, mathematical concepts are unreasonably effective in physics on the naturalistic foundations. Those are the 4 points. Or to summarize these 4 points: how does the mathematician, closer to an artist than to an explorer, by turning away from the physical world, arrive at its most appropriate descriptions? Interesting question. So let's take a look at some examples, and I'll show you some PowerPoint slides here in a moment. Mathematics is applicable to the physical world in two senses: description and discovery. Let's look at description first. Well, start with elementary mathematics, counting and measuring. All right, that's what the very basic use as we learn in our grade school work: measuring things and counting things. Now, there are things you can do with measurement. If you can measure certain things, you can measure other things that you cannot measure. Just by knowing some basic rules of mathematics, some basic theorems, you can discover what cannot be measured. It's impossible to measure. So I'm going to give you a few examples. The first one goes back to the 6th century BC, and it was developed by one of the 7 wise men of the ancients, Thales of Miletus. Thales of Miletus. He basically is the founder of what we now call deductive geometry. Euclid is one of his heirs. And so Thales did a lot of work that are precursors to Euclid. So what you're going to have to do to follow this demonstration is you're going to have to remember some of your geometry from high school. Okay, you ready for this? I want to walk through it because we have some students here that I think would appreciate it also. All right, so there's the Great Pyramid in Egypt. And so he visited that thing. Of course, at that point in time, the pyramid was reflecting the sun. There was a whitewash over limestone over it. So it was a perfectly white pyramid that reflected light from the sun. So it was just like a blinding light when you came to see it. Of course, the top was not flattened either. And that's a result of time and erosion and thieves also. So when Thales, who was a businessman, he visited Egypt, and he took back a lot of the mathematical work that the Egyptians developed. Of course, you've got to have a lot of mathematics to build this properly, right? Engineering skill. Angles to get everything working right. In fact, the first trigonometric ratio that is now called the cotangent was used here by the engineers in ancient Egypt. Of course, they didn't use the word cotangent. That was for later. Okay, so this is the situation. Thales walked by the Great Pyramid, and he said, "I can figure out the height of this thing." And the Egyptians say, "No way, you can't figure out the height of that pyramid. How are you going to do that? You got to get inside and kind of, tunnel inside and measure the distance between A and B, right? See it there? And Thales says, "No sweat, watch me." And so he looks at the pyramid. Now this is a three-dimensional attempt at a three-dimensional diagram. It's a square pyramid, so the base is a square. It's important to note that. And the apex there is just directly, B is the apex of the pyramid, directly above A. And so we have a right angle there, BAC. And what Thales did is that he took note at a certain time during the day, if the sun's out, he saw the pyramid cast a shadow. shadow was between point F and point C. All right? And he says, well, I can measure this. All right? And so what he did is he stuck a stick in the ground. Stick represented by the line segment DC there. And then he noticed that the shadow that the stick also created, and he could measure the stick and the shadow. So he's got those measurements. And he also knows we have a square pyramid. So from that, he said, I can find out the height of the pyramid. And this is how he did it. Now, what he assumed was that the rays of light coming from the sun that hit the apex of the pyramid and touched the base of the right triangle DCE, of course that's stuck straight in the ground, so it's perpendicular. That ray from the sun is parallel to this ray from the sun hitting the top of the stick. So he made that big assumption. So what we have there are two parallel lines. You already remember your geometry about two parallel lines, you know, different kinds of conclusions you can gather from that, all right? So let's walk through it. So he knew the DC, which that stick was the precursor of what we now know as a sundial, called the gnomon, and Latin for interpreter or discerner. And he also could measure, of course, CE and FC, the shadow lengths. So he knew those three lengths. He also knew this distance between A and F, okay? Because what? It's half the base of the pyramid. So all I had to do is step off one side of the pyramid, divide by 2, he's got AF. He assumed that the rays from the sun are parallel, as we've already mentioned, and we get similar triangles as a result. In other words, triangle BAC is similar, that little tilde is the symbol for similar, to triangle DCE. Let's see why he could come to that conclusion. Everybody following me so far? What's going on? Okay, let's take some analysis. What can we conclude about those two angles? BCA, right there, there's BCA, and DEC. See them? What do you think we can say about those two? Okay, they're equal. Why are they equal? Two parallel lines. Okay, we got our two parallel lines right there. We have a line here on the base, on the ground. That's the special line that's cutting the two parallel lines. It's called a transversal. So those two angles are equal because of this. Two parallel lines cut by a transversal, if that's true, then their corresponding angles are equal. Remember that from geometry? Two parallel lines, there they are, cut by a transversal. That angle is equal to this angle. The corresponding angles are equal. He also knew that angle BAC and DCE, what could he conclude about those two? Right angles, therefore they're also equal. And there's a theorem that he worked out called we now know as the angle-angle similarity theorem in high school geometry. It shows if two corresponding angles of two triangles are equal, those two triangles must be similar. Okay. And one of the key gifts that the ancient Greeks gave to us was the idea of working with proportions. They didn't work with the fractions as we normally understand fractions. They worked with ratios and proportions. And we know that from proportional analysis that we have two triangles are similar to each other, corresponding sides are proportional. All right, so I've got something I can now use to develop a proportion to find the height of the Great Pyramid. Let's let X be the height of the Great Pyramid. That's the line segment AB. And there's our proportion, see it? The ratio of the height of the pyramid to the height of the gnomon has got to be the same as the ratio of the base of the right triangle, A to C, as the base of that right triangle from C to E. Corresponding sides are proportional. Okay with that? Now let's give ourselves some data. This is fairly accurate data. Okay, the base of the pyramid is 760 feet. Let's see if our students here can pay attention, because I'll ask you a question, so watch the numbers. The length of the shadow is 260. Height of the gnomon is 6 feet. Gnomon shadow is 8 feet. Let's find the height of the pyramid. There's our proportion. Okay, what's DC equal to? What's DC? Okay, 6. All right, got it? AC, which is this length right here, AF plus FC. So FC is 260. What's AF? Half of 760, so it's 380. So 380 plus 260 will give us the next one, 640. And then CE is 8 feet. We've got what's called in the Middle Ages the law of 3. If I have a proportion, I know 3 of the 4 terms, I can find the 4th. So just make a simple substitution. There's my proportion. Now we're going to bring some algebra here. We've got to cross multiply. 8 times x will be 6 times 640. That's a law of equivalent fractions. So we get this. Divide. Now algebra comes into play. Divide both sides by 8. Before I do that complex multiplication, I can make it a lot easier. Can I cancel? What can I cancel? 8 into 640 is really nice, doesn't it? 80 times, so it's just 80 times 6, which is? So Thales was able to find the height of the Great Pyramid without ever measuring it, knowing a few measurements using mathematics. That's one of the tremendous power revelations of math. Knowing a few simple things, you can find measurements you could never measure. And of course, this plays quite nicely in astronomy. I'll just give you some practical examples. But there's the pyramid. Now, this whole situation, how many like Jules Verne's science fiction novels? You ever read Mysterious Island? Remember Captain Harding? He did the same thing to find the height of the cliff, to find his latitude at the island that they were deposited by the balloon that had kind of got lost in a storm. The whole thing that I just did here, Jules Verne walks through it in the book Mysterious Island. So you can learn some math and science fiction. Okay, the next one, also by a Greek, 3rd century BC. The Greek mathematician was named Eratosthenes. He was nicknamed Beta. He held a room in the museum in Alexandria, Egypt, and they numbered their rooms, of course, by alpha, beta, gamma, etc. And so Archimedes had the room called Alpha, and Eratosthenes had the room called Beta, so he was called Mr. Beta because that was his room. So Eratosthenes, who lived in Alexandria, noticed something, that if he traipsed on down to another city it's now called Aswan, back then it was called Siene. It's about 500 miles directly south of Alexandria. At a certain time during the year, the sun was directly above the well, as you can see by the example in the diagram. All right, rays from the sun. So he knew that at a certain time of the year that would happen. So he carefully noted that one year. Next year, same date. He didn't have any telephone or email, so he had to make these trips, you know. No internet connection, that kind of stuff. He measured the angle of the shadow created by the rays of the sun over an obelisk in Alexandria. That measured out to be approximately 7.5 degrees. So you see what he's doing here? He's doing the same thing. Rays from the sun assumed to be parallel. We got a line L1 is now parallel to line L2. We got a transversal here, T, 2 parallel lines cut by a transversal, 7.5. Alternate interior angles have to also be equal. So now we got another proportion. We have the ratio. Of course, that distance is about 500 miles. Here's what he did. There's the ratio. 7.5 degrees to 360 degrees is the same as 50 to x. Cross multiply. Divide by 7.5. Circumference of the earth, 24,000 miles. Very, very accurate for that time. Again, using some simple measurements, knowing some mathematical properties, able to discover and measure what you can't measure, at least at that point in time. 2 examples of description. I'm going to give you another example of description. You got to remember your high school algebra. All right? Solving quadratic equations. All right? General form. I'm not going to show you anything up here. ax squared plus bx plus c equals 0. Remember that vaguely? All right. What's the quadratic formula? You all have it memorized? I require all my students to memorize it. To solve that quadratic, he used a method called completing the square, which actually was done by the ancient Babylonians. Completing the square method is ancient. We just modernized it. So what's the formula? X equals minus b, plus or minus the square root of b squared minus 4ac all over 2a. Remember that? Now what have we got there? In the numerator we have the square root of b squared minus 4ac, which is what we call the discriminant. So a, b, and c, ax squared plus bx plus c. A is the coefficient of the x squared term. B is the coefficient of the x term. C is the constant. Well, if a, b, and c are certain values, that discriminant b squared minus 4ac becomes negative, and we get the square root of a negative number. And this is what mathematicians discovered in the 15th and 16th century. And they said, whoa, wait a minute. Of course, they used the quadratic formula to work with projectile motion. And they did some more work with it and played around with it. And it says, hey, this is not, we can't find the square root of a negative number, because no number times itself results in a negative number, right? What's the square root of negative 4? Okay, is it 2? Well, 2 times 2 is 4. Negative 2 times negative 2 is 4. I can't get it. So what did they do with this? Well, many mathematicians kind of just said, we'll put this aside on the shelf, not going to worry about this. But some mathematicians later on, and the mathematician I'm talking about is Leonard Euler, he said, let's just play with this and see what happens if we just let a letter equal to the square root of negative 1 and start doing some arithmetic here with the square root of negative 1. So Euler let the letter I be equal to the square root of negative 1, and then he began to work with the arithmetic. Now, if you got the quadratic formula, if that discriminant is negative, you're going to have some number plus or minus some other number that the square root of which is negative all over some other number. So you're going to have a real number component and what's now called an imaginary number component, which Carl Friedrich Gauss later said, let's call complex numbers that. And we can graph those complex numbers by, instead of the x and y axis that we've learned in Cartesian coordinate geometry, we've got the real number axis and the imaginary number axis. And Gauss began to plot things on that. The result of that work by Gauss, we have now a theory developed, both in quantum mechanics that uses that number, square root of negative 1, and we also have the theory of electricity that uses the square root of negative 1. You can't understand alternating current electricity without that number. And also, you've all seen fractal geometry. Have you all seen fractal geometry? All that's working with is complex numbers and recursive functions. So you have the beauty reflected in the art of fractal geometry. You can't turn a light on without a theory that involves square root of negative 1 involved in it, and you can't understand quantum mechanics without square root of negative 1, all out of a convenience choice by mathematicians. Let's let I be equal to square root of negative 1 and play with it. And guess what came as a result? So that's the background to these next quotes. This is a quote from a Nobel Prize winner in physics, 1963, Huygens Wigner. He says this about the usefulness of mathematics. The enormous usefulness of mathematics and the natural sciences is something bordering on the mysterious, and there is no rational explanation for it. So we've heard that before. Okay? Then he says this. We are in a position similar to that of a man who has provided a bunch of keys and who, having to open several doors in succession, always hit on the right key on the first or second trial. He became skeptical concerning the uniqueness of the coordination of the keys and doors. In other words, it wasn't just by chance here that this is working. There's some kind of design involved. Of course, if you assume chance, a chance universe, your skepticism is increased. Now, Wigner continues to express his bafflement over the fact that it is not at all natural that laws of nature exist, much less that man is able to discern them. So here's the first example that he gives, and it's involving square root negative 1. He continues, he illustrates the mysterious usefulness of mathematics by citing the application of imaginary numbers, square root negative 1, in the laws of quantum mechanics. First, he observes that the, quote unquote, the use of complex numbers is in this case not a calculation trick of applied mathematics, but comes close to being a necessity in the formulation of the laws of quantum mechanics. It has to be there in the formulation of the law. Now my slides are a little bit out of order. I'm going to show you the equation that has the square root of negative 1 in it after I walk through the second example. The second example that he gives is Newton's universal law of gravitation. Concerning the effectiveness of that law, he says, it has proved accurate beyond all reasonable explanations. So let's take a look at what Newton did to confirm his inverse square law. Remember his universal law of gravitation, two objects of mass, two different masses, multiply the masses together, and that's multiplied by what's called a gravitational constant. Divide that product by the square of the distance between the two masses. That's the force of gravity between them. So when you step on your spring scale in your bathrooms, you've got a mass, and the spring scale is measuring the force of the Earth's gravity pulling you down to its center. That's your weight. All right, and Newton's universal law governs that. It also governs the fall of the motion of the moon. So we all know about the story of Isaac kind of sitting around watching the apple supposedly hit his head. That probably didn't happen, but he noticed the fall of the apple. Looked up at the moon. He says there has to be a law that unites these two. There's got to be a law that governs the motion of the moon and the falling of an apple. Well, that was contrary to the standard line that was first developed by Aristotle many, many centuries before, that there had to be different laws governing terrestrial and celestial motion. Well, Newton was working in a biblical Christian framework over centuries that started with Athanasius, who said that there was a rational harmony in the universe, on the heavens and the earth. And so Newton was saying that rational harmony must be able to be described by using a law that I can develop a law that actually governs the fall of an object near the earth and what happens with the motion of the moon. So this is what he did. I'm going to walk you right through it. It's called the free fall of the moon. So I'm going to use some numbers here. Don't worry about the numbers. And some of these are estimates. Some of these Newton didn't know accurately at the time he was working. Some of this is in kilometers. I'm going to convert to inches. I'm going to go back and forth between British imperial and metric system. I remember I one time told my parents, some of my students, make sure your answers are in British imperial. They said, what's that? Feet and inches. Okay. We're going to assume that the orbit of the Earth is circular for our demonstration. Okay, the radius of the orbit is about that. That's a rounded figure. 384,000 kilometers. I'm using the metric system. So if I know the radius is that, I can use the formula for the circumference of the circle to find the circumference of the orbit of the moon, 2 pi r, and here's the result. And I've carried it out to some level of precision. That's the circumference of the orbit of the moon. The period of orbit is known to be about 27.32 days. Therefore, the orbital speed is 2 million divided by that. And we get that as the speed per day of the moon, 88,314, some precision there, kilometers per day. If I do some conversions on that, I get about 1 kilometer per second is the speed of the moon in its orbit around the Earth. And I've carried out the precision for a reason. Okay, everyone with me so far? That's simple, using calculators and etc. Now here's what Newton did. Here's his diagram. It's taken directly from the Principia. All right, there we've got the Earth, and we've got the orbit of the moon. Moon is identified by the letter M, Earth by the letter E, and Newton assumed that the force of gravity is acting upon the centers of both of those objects. And what we have there is, the first thing I want to note there is the arc MB. All right, see it there? The arc of the circle. That's the path of the moon. The path the moon takes under the influence of the gravity of the Earth as it makes its rotation. Again, assuming circular motion is for simplicity. Now, MA is the path of the moon if the Earth didn't exist. Take away the Earth, the moon just keeps on going. Newton's first law of motion, straight line motion, tangent to the circle, keeps on going in the direction MA. All right? And so what Newton wanted to investigate was that next one, the distance between A and B, which represents the fall of the moon with the gravity of the Earth. The Earth is pulling, all right, the moon toward itself by distance A, B. And he figured out how much that pull was in 1 second by doing some simple math. Ready for the math? All right, we're going to let x be the fall of the moon. X is AB. Distance of the Earth falls in 1 second. Enter ye old Pythagoras. Do you see a right triangle there? Okay. Triangle AME is right triangle because we have a OMA is a line that's tangent to the circle at point M, so that angle AMB right here, that angle right there has to be a right angle. So I can now use the Pythagorean theorem. I've got my hypotenuse is AE, and I got the two legs. All right? So there it is. EM squared plus MA squared equals AE squared. Now EM is equal to EB. That's the radius of the orbit of the moon. We've already established that, 384,000 kilometers. MA, we've already established that. All right, this we're talking about 1 second. So 1 kilometer per second is the distance that from M to A. That's the speed of the moon. All right, and I've carried it out to some precision there. So that's MA. AE is going to be EB. All right, this distance plus our AB, which is the fall x. Everybody okay with that? Now I'm going to do some substitutions, and there's my equation. That's a quadratic in x. If I expanded this right here, I would get a quadratic. Simplify, add, subtract terms. I'm going to do the math for you. All right. There's x. In millimeters, converted to inches, which is about 1/20th of an inch. So that's how far the moon falls in 1 second, rounded, 1/20th of an inch. But I'm going to keep the precision there on the 0.0535, et cetera, for a reason. And here it is. There's my x. There's the fall of the moon 1 second. Now, how far away is the moon from the Earth? It's 60 times away from the moon to from the radius of the Earth is about 6,371 kilometers. Take that, divide it into 384,000 kilometers. I get about 60. All right, so there's the distance. And so Newton said we got to have the square of that distance. So he applied the inverse square law, and it said this: an object near the surface of the Earth should fall in 1 second by that 1/20th of an inch, there's my decimal, times 3,600, which is the square of 60, because the force in getting it out there to the moon has been weakened by a factor of 60 times 60. That's the inverse square law applied. I got to take that and multiply 3,060 to the 1/20th of an inch. Let's go ahead and do that. We're going to carry the decimal expansion out. We get about 16 feet. So what Newton discovered there was that near the Earth, an object would fall 16 feet in 1 second. Well, Galileo already discovered that by empirical experiments. So what Newton's logic confirmed Galileo's discovery. We have one law, universal law of gravitation, governing both terrestrial and celestial motion. So that's some of the mathematics that Newton did. And he did more complex than that, but I think most of us were able to follow that, right? Okay with that? Not only by the existence of an intelligible universe, but also by the fact that the forms of thought that arise within the minds of scientists enable science to grasp the reality and intelligibility of the universe. Now, mathematics is a key player in this whole situation. I'm sure we've all went to school and we've all taken math classes and gone to university, some of us, and we always could see the math guy over there and says, that guy's, he knows how to do math. He's smart. He's one of those smart guys. He can solve those equations. And so mathematics is really a commentary on intelligibility. You have to follow a certain language in a certain way, order and operations to solve equations. So mathematics is a key player in this mystery, and I'll have a few quotes here that exemplify this. Richard Courant, a famous mathematician, early 20th century, said this: that mathematics, an emanation of the human mind, should serve so effectively for the description and understanding of the physical world is a challenging fact that has rightly attracted the concern of philosophers. Solomon Bochner, another mathematician, says what makes mathematics so effective when it enters science is a mystery of mysteries. So there is mystery compounded. John W.N. Sullivan, a philosopher, says this: why the external should obey the laws of logic, why, in fact, science should be possible, is not at all an easy question to answer. Nicolas Bourbaki, a very famous French quote-unquote mathematician, he really wasn't a person, so 5 French mathematicians in the 1950s took up the pseudonym Nicolas Bourbaki. Get to my home page, just click on the link called Mathematics, and then click on another link called Why I Wrote Mathematics is God Silent, and you'll see a link to order it. So you have to go through several levels to get to it. I apologize for not bringing a copy. I just didn't think of it. So that's pretty bad for an author not to bring a copy of his book. So there's a reason why professors are called absent-minded. So sorry for that. Okay, we're going to talk about a mystery story tonight. We all like mysteries. We all like Sherlock Holmes. We like, when I was young, I read the Hardy Boys series. I loved it. It was a page-turner. Couldn't wait till the next chapter. So we all like mysteries. And we want to find out who did it. We like the investigation. We like the evidence uncovered. We like the analysis. We like the conclusion. So we're going to talk about a grand mystery tonight, a mystery that has been a conundrum. Greetings from Washington State. You welcomed me, Denver, with a rainstorm where my airplane got sidetracked to Cheyenne, Wyoming yesterday. And we sat on the tarmac for 3 hours waiting for the okay to land into Denver. So we finally got into Denver, and then there was no gate available for the plane to park. So another 45 minutes on the tarmac in Denver. Finally got into my room a little bit after midnight last night. So if I fall asleep tonight, you know why. Regarding my website, there it is. I'm sorry for the right angle orientation of my website there, biblicalchristianworldview.net. If you go ahead and click on that link, it's on the website for the Rocky Mountain. Is it Christian Fellowship? Creation Fellowship, excuse me. RC. Okay, all right, gotcha. It's there, and you can click on it. So when you get to a great many well-known mathematicians, scientists, philosophers. And I'm going to introduce this mystery by one of the most well-known scientists, at least in the 20th century, Albert Einstein. And he said this in the 1930s, just one simple sentence. He said, "The eternal mystery of the world is its comprehensibility." He was stunned by the fact that we as scientists could understand anything about the universe. He didn't have a reason to justify the ability to comprehend the universe. So this is one example. I'll give you a few more mathematicians and scientists to substantiate what Einstein was saying. But science is basically baffled by this. philosophers of science and scientists. They're baffled